Hello, welcome to lesson 16. In this lesson, we are going to look at the Galilean telescope. A Galilean telescope is also a refracting telescope. This telescope provides an erect image of a distant object with the aid of an objective, which is a converging lens of a long focal length, and an eyepiece, which is a diverging lens of a short focal length. Let's look at the Galilean telescope in normal adjustment. In this case, a converging lens is arranged coaxially with a diverging lens such that their focal points are at the same point. Their focal points are going to be at the same point, and the converging lens, this converging lens will form a real image of a distant object at its principal focus or at its focal point f0, which is actually situated exactly at the principal focus fe of the eyepiece or of the diverging lens. You're going to see this, and then that eyepiece, so that intermediate image will then act as a virtual object for the eyepiece or for the diverging lens, which will form a final image at infinity. Let's look at this ray diagram. So rays from infinity falls onto the objective to form a real image at this position, which is actually going to be at a position f0, at the principal focus f0. That's the principal focus of the objective, and that is also going to be the principal focus of the eyepiece. So it implies that the distance from the intermediate image up to the objective is going to be fe, small f, sorry, f0. It's going to be small f0. Then this intermediate image then is going to act as a virtual object for the eyepiece, and then the final image is going to be at infinity. So it means that when the rays reach here, reach this point, they are going to be diverged, and then the image is going to be formed at infinity. So if you want to get the angular magnification or the magnifying power of this telescope in normal adjustment, we need to get the alpha and the beta, where alpha is the angle subtended by the final image onto the eye when using an optical instrument, and then beta is actually the angle subtended by the object onto the unaided eye, which is actually, for a telescope, that angle is also equal to the angle subtended by the object onto the objective of the telescope. So if I want to get alpha and beta, we know that alpha and beta are small angles in radians, so alpha is going to be opposite, is going to be approximately equal to tan alpha, which is opposite h of adjacent fe, and then beta is also going to be approximately equal to tan beta, which is h over adjacent f0, and therefore I can get the angular magnification or the magnifying power. Now m is going to be, that's the magnifying power, is going to be alpha divided by beta, but we know what alpha and beta is, and so we substitute, our m is going to be f0 over fe. So this is going to be the angular magnification of the telescope in normal adjustment. Let's make some note here. We need to note that when you look at the ray diagram, first of all, the distance between the lenses is going to be f0 minus fe, and also the image of the objective in the eyepiece or in the converging lens, sorry, in the diverging lens, which is the concave lens, that eyepiece lens, is virtual and corresponds to a position between the two lenses. Therefore, the eye ring, in this case, is inaccessible to the eye. The eye ring is inaccessible to the eye. However, the best position of the eye in this case is as close as possible to the eye piece and consequently the field of view is limited. The field of view is limited for this telescope. Let's look at the Galilean telescope with the final image at a near point. So this is quite similar to the Galilean telescope when it is in normal adjustment. Here also have a converging lens which is going to form an intermediate image, but this time the intermediate image is going to be at the principal focus of the objective, that is the objective lens, but it will be at a distance u from the eyepiece, not at FE again, but at a distance u from the eyepiece. And then that intermediate image is going to act as a virtual object for the eyepiece or the diverging lens, and then the final image is going to be formed at a near point, which is a distance d from the eyepiece. So this is the ray diagram. These ray diagrams, you need to know how to draw them because they are very, very important. They'll always ask for them. And then we should also be in position to derive the angular magnification. So when you look at this is f. You realize that my diagrams has errors about they are using capital. We are seeing that this is capital F naught. But when I talk about the distance, I said the distances are supposed to be small f naught, while the point is where the one which is supposed to be capital F naught. So this distance is going to be f naught, and then this distance is going to be u. Still, angular magnification alpha is going to be h over u, and then beta is going to be h over f naught. So we shall be having that, and then we can get the angular magnification. I've still said that alpha and beta are always small angles measured in radians, and so when we want to get the angular magnification, it's going to be alpha divided by beta, which is h over u, and then the other one is h over f naught. And when we substitute, we shall get our angular magnification as f naught over u. Then we also need to substitute for this u here. So we shall consider the action of the eyepiece lens, where the v is going to be negative d, and then the f is going to be negative fe. Negative because it's a diverging lens. The eyepiece is a diverging lens. When we substitute, we shall get our u as fe times d divided by fe minus d. And when we substitute in equation 1, we shall have f naught into brackets f minus d divided by fe times d. And I can rewrite this as f naught divided by fe into brackets fe over d minus 1. So this is the expression for the angular magnification when the final image is at a near point, or when the telescope is not in normal adjustment. Let's make a note here. When you look at that expression for the angular magnification, we have already, just go back a bit, we have already considered the sign convention here. So it means that when I'm using this formula to calculate, I don't need again to consider the sign. There is no need again to consider the sign of d and fe. Then the other thing also we need to note that when you substitute in the formula, in this formula here, and then you get a negative magnification, you just neglect the sign and take on the positive value. For example, when you get negative 24, you just take on the magnification as 24. So that's the note we have there. Let's look at the advantages of a Galilean telescope. We have different advantages of a Galilean telescope. One, a Galilean telescope, as we have seen, the image formed by a Galilean telescope is erect. That is the final image of a Galilean formed by a Galilean telescope is erect. And then also it is shorter than the terrestrial and the astronomical telescope. Let's also look at the disadvantages of the Galilean telescope. it has a small field of view, and then also it has a virtual eye ring which is not accessible to the observer. Yeah, thank you for your attention. We meet in the next lesson.